multilinear maps are denoted by um, multi of again some okay, so denoted by multilinear, this k, the field over k, I v w. Okay, so set up all such multilinear maps from like v power I. Usually just let me replace this by I, but this is just v power n only. Okay, so this is denoted by the set is denoted by this one. Now how like this permutation come into play in the multilinear maps. So for each permute, suppose sigma be a permutation of n letters. So the set of all permutation with n letters, that is I'll denote by Sn. And suppose sigma is an element of that set, so then I can actually, for each such sigma, I can actually define a corresponding, given a multilinear map, I can define another multilinear map corresponding to this sigma as follows. And it belongs to just multi k I v w and like mod I equal to n. Okay, then define sigma f of so I need to define sigma f belongs to multi k I v w is defined as sigma f of v1 up to vn, because it will take n many values, so v power n. So this is defined to be f of v sigma 1, because sigma is a permutation of n letters, so n letters mainly, namely 1 through n. Okay, so then it is v sigma 1 up to v sigma n. Okay, so this is again a multilinear maps, and for this thing we will define symmetric multilinear map. So a symmetric multilinear map or a multilinear map is called isometric, but that's better. Multilinear map from MP power I to W is called symmetric if sigma f equal to f for all sigma belongs to permutation, this permutation progression. Sigma belongs to Sn for mod I equal to n. Okay. Similarly, a multilinear map is called alternating, and just alternating if sigma f equal to sine sigma into f. So instead of just f, a sine of sigma will come. So sine of sigma is defined to be sigma is a permutation. So you can write this each permutation as product of transposition, and sine of sigma is defined as like -1 to the power number of transposition. The representation of representing any permutation by product of transposition, that is not unique, but their parity is unique. That means if it is it is either like even number of product of even number of transposition or odd number of transposition. It cannot be like you can't write a transposition as both even number and odd number, then sine of sigma will not be well defined. So sine of sigma is defined in that way. So so for alternating thing, we are like don't not wanting just sigma f to be f, but it is sine of sigma times f. Okay, so that's the only thing. Now for each such given multilinear map f, we can like symmetrize that multilinear map, as well as we can make that as a from that an alternating multilinear map also. So so that is how that is defined. So given a f belongs to multilinear map from v power I to w, the symmetrization of that is defined as SF. So SF is just sum of all over all sigma belongs to Sn and sigma of f, where again mod I equal to n, and alternation of that this f is denoted as AF. That is again also the sum over all sigma belongs to Sn, and this is sine of sigma times sigma. Okay, so then one can easily check that this is actually like if I check this like some tau belongs to Sn, then tau of AF is sine of tau of AF. That means it is alternating, and symmetry is exactly like if you use any symmetrization of that thing gives you again the same, like tau of SF will still give you SF. Okay, that is like simply a thing that if you multiply any permutation, suppose tau belongs to Sn, then sigma goes to tau sigma, that is a like bijection of Sn. So the sum is still over Sn, but one extra sign of tau will come up. That's why this will give you alternate, and here there is no sign, so that is just again still sum over Sn. So that's why it is still SF. Okay, so we'll use these things in our problem. Okay, so first problem, let's go to the first problem. So this problem is related to the purely on the permutation group. So suppose n is a natural number, non-zero natural number, and then we need to show that the number of permutation tau belongs to Sn, which commute with the permutation sigma belongs to Sn of type nu1 up to nu_n is nu1 factorial, nu1 up to nu_n factorial times 1 to the power nu1 up to n to the power nu_n. Okay, so so that means what we need to so we need to find the number of we need to find the number number of sigma belongs to Sn such that tau and sigma commutes, so sigma tau equal to tau sigma. This happens. So we need to find the number of such sigma. But what this means that sigma tau is conjugate to sigma, so sigma tau sigma inverse equal to tau. Okay, now in the permutation thing, one, like if you have for example tau is a cycle, suppose k cycle, if tau equal to suppose L1 up to Lk, a k cycle, then one can easily see that if I write the sigma tau sigma inverse, so this will be again a k cycle, and k cycle is exactly given by sigma L1 up to sigma Lk. Okay, it is easy to check that just for the if anything that is not belongs to the support of this sigma L1 sigma up to sigma Lk, that means none of this sigma Li, then it will in the right side it is just fix that thing, and on the other side tau, so then if it is not belongs to the sigma, like sigma L1 through sigma Lk, then sigma inverse of that thing, so tau will not interact that thing because the support of tau is again L1 through Lk, so this is still give you the same thing. And if it is like something in sigma L1 through sigma Lk, then suppose it is sigma Li, then under this this cycle it will send sigma Li plus 1. On the other side, sigma inverse of sigma Li will be Li, but tau of Li is Li plus 1, so that gives me again sigma Li plus 1. So in the both side you will directly see that these two are exactly the same. So in general, if you have like some not only one cycle but product of cycle, because you know each element of a Sn can be written as disjoint product of cycles, so that is the type of this means. So here the type I should mention important, that this new one type new one up to new n, this type means that there is new one numbers of one cycle, new two numbers of two cycle, and new n numbers of n cycle. But new n numbers, if it is new n is like non-zero, it should be only 1, because if there is one n cycle, like there cannot be anything else, right? So but in general it is written in this form, that it is new 1 through new n, where the new I denotes the number of bicycle. Okay, so in this case, suppose like for another example, suppose tau is some product of two cycle, one say L1 through Lk1 and another is M1 through Mk2. Okay, so so then also I can see that sigma tau sigma inverse, I can write it in like, so I can just take tau sigma inverse sigma in between of this tau, so that I'll get another, so then sigma tau sigma inverse, this I can write simply sigma L1 up to Lk1 sigma inverse sigma, because this is just identity, and then I am again writing M1 up to Mk2 and then sigma inverse. So this is identity, so this is still tau, right? So this I can clearly write. Now you apply the previous thing as before, so this this thing, because this composition is associative, so I can bracket this thing and this thing. So then again I will get, this is sigma L1 up to sigma LK1, and then this one is sigma M1 through sigma MK2, right? So from in like in general also, whenever you have this cycle or whatever cycle type of tau, if I like conjugate that tau by any sigma in that that permutation group, that will still like preserve the cycle type, right? And in our case, what we want this sigma to be like sigma tau sigma inverse is exactly tau. So if I wanted this to be like some sigma such that for this tau will be sigma tau sigma inverse equal to tau, then it should be L1 up to LK1 and M1 up to MK2, right? But this cycle and this cycle cannot be same if K1 and K2 are different, right? So this cycle must be equal to this cycle. So that means I can have sigma L1 up to sigma LK1 equal to, so this implies that sigma L1 up to sigma LK1, this is same as L1 up to LK1, and sigma M1 up to sigma MK2, this is M1 up to MK2. Now when I say this cycle equal to this cycle, that means I can have this, like I can have also this, I can write as L, say Li plus 1 and so on up to Li plus K1 minus 1, right? For any I in between 1 to K1, right? So then I can have sigma L1 equal to, if I define sigma L1 equal to, I can define any of these things like L1, L2, LK1. So I can define any of this Li to be sigma L1, and once I define sigma L1, the remaining things are already determined because that these two cycles are same. So for sigma L1 I have K1 many choices. Similarly for sigma M1 I have K2 many choices, and remaining else I can define anything that will do my job. So in this case, if I want, if my tau was given in this type, so this type, what is this type? This is like nu 1, nu 2 all are 0, only like nu K1 this is 1 and nu K2 this is 1, and remaining all are 0, right? Like not remaining all at 0, but nu 1, what if all other things are, if there is any, so nu 1 is that, so nu 1 is n minus K1 minus K2, right? So in that case, so this nu 1 many element I can define sigma for whatever for those element, and for these element I have, for one I have like K1 many choices, for this new to like this, for this one also I have K2 many choices. If I would have like K1 equal to K2, then I can also switch these two also, right? So that will actually gives me the idea of how the number of elements how to determine. So this is just a like motivational, so let me give the complete thing. So this one, so in general sigma tau sigma inverse preserves the cycle type of cycle type. So this type is also sometimes called cycle type of this sigma tau sigma inverse. So cycle type of tau, right? Now tau, as tau has cycle type nu1 up to nu n. So sigma tau sigma inverse has also cycle type nu1 up to nu n. Fine. And what the like now how do you write? So nu1 is the thing that is fixed by, so it is number of one cycle. So one cycle means all of tau fixes all of them. So I can define for those thing, I just have said that for those thing I can define this sigma to be anything. So that is just like that is any permutation between those elements. So the sigma belongs to Sn that satisfies sigma tau sigma inverse equal to tau or not the, so that satisfies this is defined such that it like for the one cycle, so it can permute like any nu1 number of elements, like it can permute nu1 number of element in whatever way it like permute nu1 numbers of element that are one cycle in tau. So new number that are one cycle in tau like with no restriction. So there are like new one factorial number of element. So that is, so this is just one, like it can permute this many things. And for the new two numbers, so there are two things. For 1-2 cycle, if it is 1-2 cycle, then I know that sigma, just from the previous discussion, that sigma can like be defined in two way, but it has like new two numbers of element. So for each such transposition you can like define in two ways. So that's why you get 2 power new 2, and also this new 2 factorial also come, because you can so there are new 2 number of like transposition, new 2 number of transpositions. So you can like permute between the transposition also. So for example, suppose you have 1 2 3 4 equal to say L1 L2 M1 M2. So here you can either take L1 L2 equal to 1 2 or L1 L2 equal to 3 4, right? So you have two choices. So similarly, if you have like new one numbers of transposition on the left side and another new two numbers of transposition in on the right side, so you can like permute in between of this permutation. You can define like L1 L2 equal to this first one, the remaining thing is, so you can permute in between these terms also. That's why you also get new to factorial also, right? So this 1 power new 1 is defined just for like just to manage the symmetry of this expression. 1 power new 1 is just 1 anyway, with no restriction. And so, and in general, and new I new I number of I cycle. So new I number of cycles can permute in new I factorial ways. In between them, and like with each I cycle is also permute in itself in I many ways. Hence the number of sigma belongs to Sn such that sigma tau sigma inverse equal to tau is like, for first one you have new 1 factorial, similarly for second you have new 2 factorial, but also between you have like 2 new 2 numbers of, for each transposition you have 2 representation of this thing, so that is also same. So you have 2 power new 2, similarly like new I factorial into I power new I, and all the way up to new n factorial, n power new n. Okay, so that is in given representation it is new 1 factorial, new 2 factorial up to new n factorial, 1 power new 1, 2 power new 2, n power new n. Okay, so is this clear, or are there any confusion? Okay, so then let me go to the next question. So it is again related to the permutation. So here you need to find the number of involution. So involution means it satisfies the equation like sigma square equal to identity, where sigma compose sigma square means sigma compose sigma equal to identity. So in S2n, fine. So and not only this involution, involution has no fixed point. That means the number of one cycle is 0. So that means exactly that whenever you don't have fixed point, so this implies the order of this sigma is exactly 2. So we need to find all those permutation sigma which is of order 2, and it consists of 0 1 cycle. So it is exactly n many the order of his permutation is the LCM of the order of the disjoint cycles, right? So in this case, as we know that any like so 2 LCM of all those things is 2, but there cannot be any one cycle. So all the transposition of sigma will have exactly n many transposition, because if it is as less than n many transposition, then we must have some one cycle. It cannot have more than one cycle, because then the sigma square equal to identity will not be satisfied. So we write that. So sigma square equal to identity, this will imply that sigma has sigma has at most order 2, because if sigma is not equal to identity, then sigma has order 2. So this implies sigma equal to identity, or sigma is of order is of product of disjoint transposition. Disjoint transposition. Positions, but as but if sigma has no fixed point, if sigma has no fixed point, for identity everything is fixed, right? So has no fixed point, then sigma cannot be identity. Sigma is not equal to identity, and also sigma is product of exactly in many disjoint transpositions. Okay, so we need to find all those sigma belongs to S2n such that it is product of n many disjoint transposition. Okay, so that's so this we need to find number of sigma belongs to S2n which are product of n many disjoint transposition. Positions. Okay, so now how do you find such thing? So you have 2n many letters, so I can permute that thing by in 2n factorial many ways, right? And if I put consecutive brackets, two brackets between two things, for example suppose suppose let's say L1, L2, L3, L4, L2n minus 1, L2n. If I just write this L1, L2, L3, all those belongs to some 1 through 2n numbers, and then if I just put the bracket in between them in this way, so that gives me a like disjoint product of disjoint n many transposition, right? And that's what we wanted. But here the like common thing is that I can have for example I can also have write this is same as L3, L4, L1, L2, and all those things are suppose same 2n minus 1, L2n. So this is also same as the previous one. So for example let me just give it. So 1, 2, 3, 4, 5, 6. So this is I'm suppose considering S6. So then you have product of 3 transposition. This is a like element, but if you have the like another permutation which you have 3, 4, 1, 2, 5, 6. So this is also same as the previous one, right? So I can like permute the transposition this 1, 2, 3, 4, 5, 6 in between in factorial 3 many ways. And also I could have this is also same as 2, 1, 3, 4, 5, 6, right? So also the like I can permute the terms inside the transposition. For each one I can permute in 2 ways. So as there are n many transpositions, so I have 2 power n many ways. So for one such L1, L2, L1, L2, L3, L4, L2n minus 1, L2n like product of n many transposition, you have 2 power n into factorial n many is equal like representation for same this permutation. So for each such permutation you have that many like factorial n into 2 power n many same representation. So I have to quotient out by those from the total number of representation of 2n numbers of element. So that's how we get this the total number as 2n factorial by this thing. Okay, so this is equivalent to like number of permutations with 2n letters quotient out by equivalent quotient out by equivalent relation for product of equivalent relation, not relation, representation for product of n transpositions. So number of the permutation with 2n letters, that is factorial, so 2n factorial. And just discussed that an equivalent representation for any n transposition from this 2n factorial, this thing is like factorial n into 2 power n. Factorial n comes because you have n many transposition, you can permute in between permute between them in factorial n many ways. And 2 power n comes because for each transposition you have like 2 representation. You can either write like L1 L2 or L2 L1. So there are n many such transpositions, so for each one you have 2, so total you have 2 power n. Okay. Okay, so this is the total number of the required number of involution without fixed point. Now let's see the number of involution with without any restriction. It can have fixed point, it cannot, it may not have fixed point, it may have fixed point. So this is exactly comes from the previous thing, that you sum up all such involution with 2k numbers of without any fixed point, remaining are fixed. So just suppose sk is not sk, let pk be the the number of transposition, number of involution, involutions with n minus 2k many fixed point. N minus 2k many fixed points. That means these 2k elements are this is product of k many transposition, and remaining things are fixed, many fixed points. Fixed points. Then by previous thing, previous problem, this pk equal to the okay, so there this n choose 2k comes because I can choose this n minus 2k many elements, or 2k many elements which will not be fixed by that involution. So that is I can choose from the n many elements by n choose 2k ways. So that's how why this n choose 2k come. And for each such choice you have to just from the previous thing, you have 2k factorial by k factorial into 2 power k many involution. So this number comes from because it has k many product of k many transposition. So that number is 2k factorial by factorial k into 2 power k, and n choose 2k comes because you have you can choose your 2k many elements from the n elements in n choose 2k ways. Okay, and then you just add all those things. Hence the required number is sum over k greater equal to 0, and obviously 2k less equal to n choose 2k factorial by k factorial into 2 power k. Okay, so this is just a kind of corollary of this thing. Now let's go to the next one. So here also we need to find the number of permutation in Sn whose canonical decomposition, that means if we write that permutation as product of disjoint cycles that contains a cycle of length n greater than cycle of length greater than n by 2, that number is factorial n into this thing. So this thing is once you have a cycle of length n by 2 greater than, so there is exactly one, there cannot be like more than one cycle of length greater than n by 2, because the total number of element is bounded by n, right? So cycle cannot be, two cycle cannot be of a length n by 2. Now what we have, so the choice again is you have to choose, like suppose there is you can choose your k, k is any n by 2, like greater than n by 2, but it cannot be bigger than n also. So n, then this k many elements you have to choose from n elements, which will be your like this which will consist in your permutation of like just a cycle, as a cycle. Then the number of k cycles in Sn is, so it will be just n choose, like I can choose any k elements from n elements, so n choose k, this many. But there is this choice is also involved, like if I choose 1 2 3 4 5, then this one is also it's same as 2 3 4 5 6, right? So but not all of these things. So this is choose, this I should not write as choose, but as permutation, like as a combination. So not is as permutation. So npk, so npk means factorial n by n minus k factorial. But for each of these thing you have the like canonical rotation, right? So rotation, the 1 2 3 4 5 is same as this cycle is same as 2 3 4 5 1 and so on, right? So there are five things are same. So you also have 1 by k. So this many k cycle you can have in your like in Sn, just k cycle. But the other thing is, no, there is no restriction on that thing. So there you can have remaining n minus k elements are remaining, so that those thing can be any permutation of the remaining letters. So there are like n also, there are n minus k many free elements which will give us n minus k factorial many elements, like n minus k factorial many elements of Sn. Hence there are like for each such k cycle I can like choose any n minus k factorial many permutation with the remaining n minus k letters, right? So there are sum over all such. So for each fixed k I have this many. So so there are n factorial into k into n minus k factorial into n minus k factorial many, that means n factorial by k many many permutation in Sn consist of a cycle of length k, and hence the total number is sum over all such. hence the total number is sum over n by 2 k is equal to n factorial n by k. Okay, so this is the thing here. So next one is again you need to find the number of transposition like number of permutation in sigma n without any fixed point. So here the process is by you can use the principal inclusion exclusion. Suppose let's say pi denotes the set of all permutation in so this is again Sn. Okay, this is just Sn. So in Sn that fixes only I, that fixes I belongs to 1 to this n. Okay, so this pi is defined for 1 through n. Then what is, like, if I have pi1 intersection pik, so this means that this consists of all permutation which fixes I1 I2 all the way up to ik, right? So now you can like calculate the number of permutation which fixes at least one of the I1 through In by, so what is that set? So that is the cardinality of this set P1 union Pn, right? So this is means that all the permutation which fixes at least one of 1 through n, and this is by principle of inclusion exclusion. This is sum over all, like I belongs to 1 to n pi, and then this is sum over all I less than j and ij in between 1 through n pi intersection pj, and all the way up to minus 1 to the power n n minus 1 p1 intersection pn. Now if you have this pi, if it fixes like only one elements, so the remaining n minus 1 elements are 3. So there are n minus 1 factorial many elements, and the one element that I choose initially, that I can choose from the n elements in n choose one way. So for each pi, so here cardinality of for any I, this pi is n choose 1 into n minus 1 factorial. So that means it is just n factorial by 1 factorial, right? That means n factorial. And similarly, if I have pi1 intersection pik, so that will fix k many elements. So remaining n minus k elements, I can have n minus k factorial many permutation for those, and I can choose those n minus k elements in n choose k many ways, right? So this is n choose k into n minus k factorial. So this is again n factorial by k factorial. So from this one, so I will get that this is just sum of minus 1 to the power, like okay, I equal to 1 to n minus 1 to the power I plus 1 n factorial by I factorial. Okay, I factorial, right? Yes, I factorial. But this is the complement number that we wanted. In our case, we want the number of permutation without any fixed point, and this counts at least one fixed point, right? So the required number is just the total number minus this number, hence the required number is factorial n minus this thing, 1 to n minus 1 to the power I plus 1 factorial n by I factorial. So this is, I can just factorial n, this I can just include as so it is in terms of k, so I can write k equal to 0 to n minus 1 to the power k, because minus of this thing minus of I minus 1 to the power I plus 1 is just I, and so this is the required number in this case. So it is already it's over time over, so I'll write this thing in the PDF, and I'll upload in the Google Sheet as well as in the YouTube video in the description box also. Please check there. Just let me give a like what was mean like asked in these questions. So there two maps P1 and P2 are defined from the set of all multilinear function from V power I to W. One is just divided by factorial n into SF, and another is 1 by factorial into SF of the function and this is alternation of the function f. Okay, so then this P1 and P2 are well defined map. I need to show that their projection. So if you just compose these two times, that gives you the same thing. So it is easy because this S of SF is already a symmetric multilinear function. So if you again symmetrize that, so for each such like permutation, sigma of SF is still SF. So as there are factorial n many ways, so the factorial n and factorial will get cancelled, and it will get the like P1 square equal to P1. Similarly for P2. Okay, and in the second question you are given that, so one thing that in this case the characteristic of k cannot be less than like less equal to n, because 1 by factorial n is there, otherwise it will be like undefined, right? So that's why this characteristic thing needed here. And in this case also this characteristic of k not equal to 2, because I'm dealing with the only bilinear maps, so that this half of 2 is this like well defined. Okay, so in this case also just the once you have the projection map, so you can again just take n equal to 2, and you have projection, this P1 P2 both are projection, and one can also easily see that the like the kernel of this P1 is image of P2. Okay, so from there you know that whenever you have projection, you can like decompose your domain in direct sum of two spaces as the kernel and image of that thing. So but in this case actually the kernel the like, not kernel and image, because this thing is not exactly from the okay, you can think this P1 as not as symmetric of this thing, but as just multilinear IVW to multilinear IVW. So and next maps, that is alternating, you know, when the like sigma of f equal to sine of sigma into f, but a alternating definition of that thing is when the like two terms any two terms are equal, then that should be 0. So that is equivalent condition that is proved in class. But in this case also it is saying that you don't need also to check any two arbitrary position, you only enough to check that if two consecutive terms are equal, then if it is 0, then it is also alternating. Okay, so that is again like the one step more general thing for the alternating thing. because alternating, if you check for the all the sigma, it is like for bigger n it is factorial n many elements you need to check. But in this problem you are it is saying that you don't have to check for factorial n many numbers. It is enough to check for like only n minus 1 many terms. If it is for n minus 1 many terms, if the function is vanishing, then you can directly say that is alternating. Okay, and or like next thing is just using this problem, it is you need to show that this function that is defined through like one alternating multilinear function and another is just a k-linear map, like defined through that in this fashion, that is alternating. So I will just use this problem to show that this is alternating. Okay, so this is the all the problem which I wanted to discuss. So I'll write this problem and upload anyway. So let me stop here if there is no other question.
Thank you, sir.
Okay, so then we'll stop here today, and we'll like, next week will last tutorial session. And okay, so bye for